Good morning, everyone. So welcome to today's class. Last class, we just have a very short start in the digital image processing. And for this class, we will see actually lots of the image processing methods. But let's just try to finish how to read, how to save the images in the Google Cloud first, so that later on you can know how to manipulate the images. So we learned how to read the image in Cloud. Basically, if we just want to have some very simple manipulation or very simple methods, we can directly use this matplot library, import this, and actually this already provides many powerful functions, like read image, the most basic one. And actually, through this ImRead, this function, we can see that there are three types of images. Basically, it will decide what is the shape of the array it returned of this read. So it possibly return these three shapes. If it's a grayscale image, it will return numpy array with the shape mn, because now each pixel only has one intensity value. And if it's an RGB image, then it will return MN3, because now we have three channels, red, green, and blue. Actually, we have a third type, the RGBA image, MN4, this shape. So except from the RGB, it has another channel, alpha, so which represents the transparency of the image. Usually, we only refer to these two types of images, but still we should know that actually there is some RGBA image, especially if you want to represent the transparency information. And then the value in such array, we also talk about that in some standard format, we know that the images are some 8-bit data. 8-bit data means that it has possibly 256 values. So usually it's just some integers from the range 0 to 255, except for the PNG image. PNG image, you can regard it as some compressed image. So starting from some standard format of image, compress it so that all the values are normalized into the range 0 to 1. And these values are float values, so we can have some decimals here in this PNG image. So this would be like how to read the image. And after read the image, all the images, if you use this matplot library, all the images become some numpy arrays. And then how to show the image if you already have the numpy array. So basically that's a reverse function with this read image, right? So in this case, we can still use this library, and there is a function called the imshow. In this imshow, you can just give a numpy array to this function and let it show the image. And the syntax would be, first you need to give an array x. So this x represents the image data. And the supported array shapes, again, we only have these three supported array shapes because we only have these three possible types of images. If it's a grayscale image, then the shape, you should pass it to MN, means that, okay, now this is a grayscale image. Actually, these values can be mapped to some colors. That means even though each of the pixels now only contains one value, and by default, of course, it's some grayscale, but if we just use these intensity values map to some colors, then actually we can have some color map. I think you have done some similar things in lab 1. So even though you only have one value in each pixel, actually if you map it to red channel, green channel, blue channel, you will have some color map images. The second supported array shape, MN3, of course, that means you give it RGB values. And all these values, it can be 0 to 1 float values. That means it's a PNG image. Or if you give it 0 to 255 integers, then that means this is a standard format of image. Then the third supported array shapes would be MN4. So basically just equipped with another channel alpha representing the transparency. So know that for this imshow, this method, it only supports these three array shapes. So if you have some 4D, 5D, multi-dimensional arrays, that it cannot support because that's not digital images. And if the number of channels, you let it be some values, not 3, not 4, it's not supported. because for digital imagery, we can only have like 3 channels or 4 channels. And of course, the first 2 dimensions, MN, always define the rows and columns of the imagery. That's the image size. We have some other arguments here, as you can see, CMAP, WeMean, and WeMax. Here the CMAP means the color map. For example, if you let it to be gray, then that means you just want some gray scale in these intensity values. Actually, this color map can be some other channels, like you can let it be red or green or blue. So this is basically the color map, and you can let it be some string values that's supported by the Matplotlib library. But this parameter is ignored if we use RGB or RGBA data. So basically, this CMAP only effective if you give this method a 2D array. 2D array means that the shape is MN. In this case, each pixel only has 1 value, so that's why this value can be mapped into some color map. But if your image is already RGB or RGBA data, then this parameter is just ignored by default. So whatever you give, it just ignore it. And then we have some other arguments, as you can see here, WeMean and WeMax. WeMean and WeMax actually means the minimum and maximum possible value in all of the pixels. So by default, this method ensures will scale the elements of the NumPy array you pass to it so that the smallest element becomes 0 and the largest becomes 1. As you can see, it's a normalization, right? Normalize all of the pixel values into 0 to 1. All the intermediate values just map to this value range by some linear function, which is very similar to the KNN question you have done in the midterm. You have a minimum value, a max value, and then do this linear mapping. But optionally, actually, you can give the value to WeMean and WeMax. In this case, all the elements of the array, if the value is smaller or equal to WeMean, they will be mapped to 0. And all elements greater or equal to the WeMax will just directly be set to 1. And then the elements between WeMean and WeMax will be mapped in the linear function into this interval 0 to 1. So for example, you can imagine that you give an input image and you set the WeMean to be 50. In this case, some pixels actually have the value below 50, and in that case, all these pixels will directly set the value 0. And all the, like between WeMean and WeMax, these values will do the linear mapping. And this mapping will be 0 to 1. That means after you pass an image, pass an array to this imshow, actually all of the showed image will be PNG image. So by default, this Matplotlib library, if you ask it to show some image, it will show some PNG image, the compressed image, because inside this function, it will just do this normalization to 0 to 1. Of course, this can save lots of memory, right? Now all the values are just compressed to 0 to 1. So this is the imshow method. And then the return value is just an image, so it will plot the image for you in some axis. So that's why it's called axis image, because the images will be attached to some axis, and this axis actually is the image coordinate system. The last function is save. How to save an image? We can directly use this method in save. And basically, we only need to give these 2 arguments. The fname is the path or some file-like object that you want to store your image in. You just give it the path. And this array is the image data. We know all the images in the Matplotlib library are just some NumPy arrays. So you give this array, and then it means that you want the plot, this library, to save the image from such array. And know that in this case, of course, we have some restrictions on the array shape. Again, this shape can only be these 3 shapes. It can be M by N, that means the intensity or the luminance, or M by n by 3, the RGB, or m by n by 4 RGBA. And the first two dimensions, mn always define the rows and columns of the image. So this is how to save. So these are some very basic functions, and we can see some examples here. As shown now, we already have mounted our Google Drive, and also we have added the path for the interpreter to search. So in our Google Drive, suppose we already stored an image there, this image, the Snorlax, the Kabigong image, and then we can try to read it. So let the img, this array, be in read snorlax.png. This is the image we already stored in our Google Drive, and then we can use this imshow to show the image, and then we can get a shoot image like this. So know that this image is already attached to some axis, and this is the image coordinate system. Image coordinate system means that x increase from left to right and y increase from top to bottom. The original point actually is at the left top corner, as you can see. And actually, it also indicates the dimensions of this image. As you can see, the dimensions is here. It's 10,000, just at this part. 10,000 by 16,000 by 4. So means that it's a RGBA image, right? It has 4 channels, and also the width is 1600, the height is 1000, and actually the total number of pixels can also be calculated there. And then we can find the shape. In this case, like height width layers be this img.shape, and we can also print all the required information just using this. And at the end, we can also try to save the image. Until now, actually, we haven't done any manipulation, haven't done any processing to this image, but we can directly save it. Use this imsave and save it to be another file name called snorlax2.png. And after that, we save a new image, even though it's the same way the previous one. So this will be some very basic functions, how we can use the matplotlib library to read, to show, and to save an image. So until now, any questions? Great. Yeah, those are very basic elements. Then we can start to learn some image processing, because now we already know how to access some images. The first thing I would like to introduce is a library, OpenCV. Later on, almost all the image processing we won't implement by scratch. Even some of them we will try to implement from scratch, but most of them we will directly use the OpenCV's functions. So OpenCV, the full name is the Open Source Computer Vision Library. It's an open source computer vision and machine learning software library. It was built to provide some common infrastructure for the CV applications, and also to accelerate the use of machine learning in the commercial products. And know that actually, this library has already more than 2,500 optimized algorithms related with CV, includes a comprehensive set of both like classic and even some of the state-of-the-art computer vision and machine learning algorithms. That's why when we want to deal with some CV tasks, usually we directly turn to the OpenCV, because almost all the algorithms about CV, about image processing are already implemented there. You can directly use it. So another good property of OpenCV is that actually it supports a wide variety of programming languages, not only restricted to Python. If you use C++ or Java, actually you can also use OpenCV, but of course the syntax will be somehow different. But actually the OpenCV supports this wide range of the programming languages. And in this course, we will teach some of the very classical algorithm in OpenCV and how you can apply it in the Python, because like our course, the whole course is based on the Python. So first, the image processing is about convert the color image to grayscale. We know that the color image has like more channels than grayscale. Grayscale, we only need one value for each pixel, but RGB, or the color images, actually for each pixel it has 3 values. So that means the color images contains more information, and more information means that it consumes more memory. And in some programs, we find that actually it's okay, it's even useful to lose some unnecessary information to reduce the space and computational complexity. In that case, we want to perform such processing. We want to convert some colored images to grayscale images, because in some tasks we find that actually the color information is not necessary to recognize and interpret an image. You can just imagine that the handwritten digit recognition task we have done before. For example, just suppose that if the data are collected from some users and the users use different colors to write the handwritten digits. Some may use some black pen, some use blue pen, some use red pen. Actually, all this color information is not useful, not necessary for us or for the neural network to identify the handwritten digits, right? Red 8 and black 8, basically they are all 8s. They should be classified into 8. In this case, the color information is not necessary, and that's why we want to reduce such information, because we want to save some memory. We don't need all of this color information in that task. And actually, that's why the MNIST data set is some grayscale images. Basically, the color is not useful. And the grayscale, in this case, can be good enough for recognizing some certain objects. The color images, of course, contains more information than black and white. But in this case, they just add some unnecessary complexity and take up more space in the memory. So we can just try to perform this one. This is example. Suppose we have a color image of a cat. Then after grayscale conversion, we should convert it into such a grayscale image. But how to do that? Right? How to combine the three values in RGB, 3 channels, into a single value. Here we have some formula to that. So this is one way. Note that actually there are multiple ways to convert color image to grayscale image, basically by adjusting the weights here. But this is a very classical way to convert color image to grayscale. As you can see, the final value V is some weighted sum of RGB values, and we assign the weight of red channel to be 0.299, and the green channel, this weight is 0.587, and the blue channel had the weight 0.114. Of course, if you adjust the different weight values, you will get some different conversion. And this is one of the most widely accepted conversion. If we want to implement this thing, actually it's very easy to implement if you want to implement from scratch, right? Basically, you just implement one line of Python code for this weighted sum. But somehow we are so lazy. Even for this very simple formula, we want to use OpenCV to implement that. Then we can import the OpenCV first. In OpenCV's Python importing, the name is CV2. So if you want to import OpenCV, directly use this line of code import CV2. After that, you can access all of the functions, the modules, the classes in OpenCV. Here, if we want to convert color to grayscale, we use this method CV2color. The syntax would be like this. First, you need to give some input image. This image is the image that you want to process, and of course it should be some color image, because now you want to convert it into some grayscale image. And this code is some conversion code for the color space. And if you want to convert RGB to grayscale, you need to give the correct and specific code. In this case, the code is called this one, CV2.color RGB to gray. And after you specify the code, the conversion code is like this. This method CV2color accepts that, okay, now I should perform the function of converting from color image to grayscale image, and it will return a converted image just by your specified code here. So let's see the effects. So again, we already mounted our Google Drive. Just suppose everything is done, the path is correct, and we read our snowlegs.png and show it here. So this is our PNG, snowlegs.png. We have this polygon here. And after that, we can convert the color image to gray by using the CV2. So note that we already import CV2 here. And then we get a new image, gray image, which is from CV2.CV2 color. Give image as an input and use this code color RGB to gray. After that, we can show the image. In this case, we get an image like here. Note that because it's a grayscale image, so you need to assign the same map. Because now each pixel only has one value, so you need to tell the function which color map you want it to show all these intensity values. If you want to show grayscale, just let the scene map be gray, and then we get an image like this. Basically, it's directly from the previous images. So of course, the image size will be the same. Right, so still it's like 16,000 by 10,000, 1600 by 1000, but all of the pixels now only have one value, the grayscale intensities, and then we can save this new image using this imsave function. So we get a snowlegsgray.png. This is one of the most basic and most simple image processing. Directly convert some color image into grayscale image. So any questions so far regarding this one? Alright, so then we can go into the next one. Yeah, just now we have seen an easy one, but there are sometimes more complex image processing, and this is called the image affine transformation. Note that it's not single image processing method. Actually, this is a general type of the image processing. They are called the affine transformation. Note that affine transformation actually is a concept from the mathematics. So if we're talking about affine transformation, then basically we mean the transformation that preserve the collinearity, the parallelism, as well as the ratio of distances between the points. Note that it does not need to maintain the distance between points, but it must maintain the ratio of distances between the points. So for example, after an affine transformation, the midpoint of a line should remain the midpoint after the transformation. You must keep the ratio, but actually the distance does not need to be like kept. So it's okay to scale it, but the ratio must be kept. This is a concept in mathematics, in geometry. And when we apply it in the image processing, we will find that actually this concept is very useful. And for all the affine transformation, it does not necessarily preserve distances and angles. Actually, distances and angles, they can all change in such a affine transformation. And some geometric transformations, such as this commonly seen translation, rotation, scaling, shearing, these transformations are all affine transformation because actually they can keep the collinearity, the parallelism, and also the ratio. And in general, if we want to represent the affine transformation using some mathematical formula, we can express in the form of a linear transformation followed by a vector addition. That means for any pixel, x, y, we know each pixel is specified by a coordinate, right? So any pixel x, y, if we want to apply some affine transformation and suppose the resulting coordinates, because basically is that you want to change a pixel into some new coordinate, and suppose the new coordinate is x prime, y prime, the new coordinate, and then the relation between new coordinate and old coordinate should follow such mathematical formula. So it's a linear transformation, so that means we have a 2 by 2 matrix here. And basically, it's the matrix multiplication between this matrix with the original coordinate x, y, and then add a vector, this vector b0, 0, and b1, 0. Any transformation can satisfy such mathematical formula is the affine transformation. And any affine transformation can be represented using such formula, but of course they will have different A values and B values. We can try to rewrite it a little bit, and after rewriting it, we find that basically this one, after matrix multiplication and vector addition, the first entry should be this A00x plus A01y plus B00, and the second entry we can also have some similar results here. And then we further rewrite this vector. We find that actually it's a matrix multiplication between a 2×3 matrix here with such a vector. Such a vector is the original coordinate x, y, then concatenate with another entry 1 so that it becomes a vector with length 3. So actually this equal with this matrix multiplication. Okay, now we already get the relation between the new coordinate with the old coordinate. Like how can we get x prime, y prime if we already have x, y? So basically for each pixel x, y in the original image, we just do such transformation. In this case, as long as we know what is this matrix, then we can perform the affine transformation. So this is equivalent to defining such affine transformation, and we call it big M. So this matrix, big M, is called the transformation matrix. To define what transformation you want to do, you need to first define what is this big M. And of course, if you have different big M, if you change any of these values in big M, then the affine transformation will also change accordingly. Each M corresponds to one affine transformation. This is the general representation of the image affine transformation. Then let's see some specific examples. The first is translation. So translation, if you directly want to apply the translation, actually even if you don't know anything about an image affine transformation, you can still use CV2. CV2, we use this swap affine method, but in this case, you still need to give an argument called M, and this M is exactly the M here, the transformation matrix. So for this SRC, it represents source. This source means that the input image you want the OpenCV to do the transformation for you. And M is the transformation matrix. And by definition, any transformation matrix must have the shape 2×3. As we derived here, it must be a matrix with the shape 2×3. And the D size, this argument is the size of the output image. So actually, it's not necessary to be the same with the input image. You can define what is the output image size. And here the flags. Flags, actually, this is indeed important in image processing, but somehow we won't cover it in our course. This flags means the combination of the interpolation methods, and actually we also have this border mode, which is a pixel extrapolation method. In our course, we won't cover the interpolation and extrapolation method. I think in some more advanced CV course, actually you will learn how to do interpolation and extrapolation. So the rough explanation about interpolation and extrapolation is that after some affine transformation, or possibly after some transformation, you will find that some pixels cannot find some original corresponding pixels. That means some new pixels occur in the new image. In that case, how to assign the values for the new pixels will be dependent on the interpolation or extrapolation method. Basically, it's try to get the value from some neighboring pixels, but we won't cover too much in this case. And for the border value, is the value used in case of constant border, and by default it's 0. This is actually related with this border mode, the pixel extrapolation method. A very simple example is that you can consider if we want to do the translation. For example, if our previous image is like this, so this is the image, and suppose we want to do translation. After we translate it by some pixels, we get a new image like this. Maybe not a good to keep it more formal. So we get a new image like this, right? But the image coordinate does not change. Image coordinate means that the original point is here. This is 0, 0. But somehow after translation, actually the image is like this, but these pixels in the new image, these pixels, they seems becomes empty because they don't have the corresponding original pixels. Like actually, if there is more pixels here, then this part will be translated to here. But somehow this does not exist. So actually, these are some new pixels. The border pixels, they will possibly just create some new border pixels. In this case, how to assign values for these new pixels is called extrapolation. And for simplicity, most of the cases, we just set all of the new pixels, especially in the border, to some constants. And here, by default, is 0. So that means by default, we will just set black to all of these new pixels. If their values is 0, then basically that's black. This is for like some new pixels, especially like occurring in the border. Later on, we will see the example so that you know it will be set to some black colors. So after this warp affine, it returns the output image that has the size, this size is what we specified here, and also the same type as source. So it's the same type, means that if your source is some like grayscale image, then after this affine transformation, it's still grayscale image. If it's color image, then after this transformation, it's still color image. So the affine transformation won't change the type of the image. It only changes the coordinate of the image. And then we need to know the big M, right? So for the image translation, we know that translation is simply shifting of the object location. And suppose we have a point xy, and which is translated by this value tx, ty. And suppose now the new coordinates after the translation is x prime, p prime. Basically, if you look at this image, you can easily see that. Suppose previously we have a point here. Then after this translation, it will becomes this place. So it's just simple this translation. In this case, we can easily derive the relation between new coordinate and old coordinate. New coordinate x prime should be x plus tx because we shift tx this distance, and this new coordinate y prime will be the old y plus ty. We shift such small value ty. But even at this moment, we haven't finished it, because if we want to define a affine transformation, we must rewrite it into the matrix multiplication form. We must find what is this M. So if we want to rewrite it into matrix multiplication form, we will get this thing. So x prime, y prime, this vector comes from the matrix multiplication between M here. This M is 1, 0 tx, 0, 1 ty, and multiplied with this vector x, y, 1. Only at this step, we get what is this big M, and then we can perform the affine transformation. So this is how we do that. We read the image again, the Snorlax PNG, and because now we just want to show how to do this translation, so we directly first convert it into grayscale image and show here. This is the grayscale version of our Snorlax.png. And then we can find the shape of the grayscale image. The shape is directly get the rows column which come from the gray image dot shape. Alright, after that, we can perform the affine transformation to do the translation. We first need to define what is this big M. Big M, we know that it takes this form. Basically, we just substitute tx and ty with the number of pixels we want to shift. Suppose now we want to shift like 100 in the row, in the column direction, and shift 50 in the row direction. So that means this M is 1, 0, 100, 0, 1, 50. And then after that, we perform the transformation. We use the syntax here. This warp affine. So we let the source be the gray image, M be this big M we just formulated here, and the size the output image size will be the columns rows. And note that this is a little bit confusing for some of you if you look into it. So it's better I explain it here. If you get the shape from the gray image, you get the rows and columns. But if you get the image size in this CV2 web file, you get columns, rows. Yes, it's confusing, but we have nothing to do. This is because Matplotlib library and OpenCV use different coordinate, different interpretation of the size. Basically, in Matplotlib library, after you get the image shape, the first one represents rows, that's the height. The second one represents column, that's the width. But in OpenCV, somehow it's reverse. In OpenCV, the image shape, the first one is the columns, the width, but the second one is rows, the height. Actually, the two libraries just use the reverse size to interpret the image shape. So yeah, so note that if you are using Matplotlib library together with OpenCV to process an image, just pay attention to this part. Actually, their shape is reverse between the columns and rows. Yeah, I know this is somehow confusing, but yeah, it's better that they can be consistent, but they are not consistent. All right, so that's why here in this D size, output image size, we let it to the columns rows because the OpenCV accepts that the first dimension is column. All right, and after that, we can show the image. This translate IMG, and we show it here. So we can observe that after this translation, the original image is translated, right? The shifted 100 pixels in this x-axis or in this y direction. So as you can see, now it's get 100 shifting, and in this y-axis or in this height direction is shifted 50 here. And of course now there are some new pixels. That's this border and this border. By default, OpenCV will just directly set them to be value 0. That's why these two borders actually they are all black because they directly accept the value of 0. And of course, there are some pixels missing because we said the output image has exactly the same size with the input image. So suppose it should have like larger dimension like here, right? But some pixels are missing, but actually we can also represent them if we set it to be different size. But the new pixels will always like get the value 0 by default. So this is for the image translation. So any questions so far regarding image translation? Great. Then we have some more affine transformation to show you. The second is image reflection. So reflection refers to that we want to do some mirroring or flipping the images along some axis, like it can be horizontal or vertical axis, and to make sure the resulting image face the image coordinate. Note that after flipping image along x-axis, we need to translate it by the amount of the number of rows in y-axis. And similarly, if we want to flip it along y-axis, we need to translate it by the amount of columns in x-axis. And we can use some simple question to a simple example to show you. Suppose this is a original image. Yeah. So sorry, I want to draw to make it asymmetric so that you can know the effects of reflection. Okay, maybe to get it something like this. Alright, so suppose this is our original image, and note that original image, the original point is always here, 0, 0, top left. And now suppose we want to flip it along the x-axis, and we know that maybe use another color for this coordinate. This one. This is the x-axis, this is the y. And if we want to do the flipping, right, then the resulting image actually will become this way. This is a reflection. So this is the reflection along the x-axis. But note that if you just put the image at there, it's not legal, because now the y coordinate is negative. Because the original point is always here, we already set the original point here. That's at the top left corner of the old image. So after reflection, you put it into some negative part of the y-axis, then you have to do some translation to move it downward. So that's why we see that actually after the flipping, we need to translate it by the amount of the number of rows in y-axis. So that means after that, after you have a resulting image there, reflection, you still need to translate it back. Alright, so in this case, we can just, to get the relation between the new coordinate with the old coordinate. Suppose we have some point x, y, which is reflected along the x-axis. Suppose this x, y is here. Just consider this point is xy. Then after reflection, it will become this point. Right? So we know that this point, the coordinates should be x negative y. But somehow after the translation, because we need to move it back, we must move it below to let it fit the legal coordinate system. So after this translating, this point actually will becomes this one. So that means now it becomes x negative y plus the rows minus 1. Rows minus 1 because we think that the rows, actually the index starts from 0. That means we must shift it back by the number of rows so that everything is in the legal range of the coordinate system. In that case, we find that for any point x, y, if we want to do the reflection along x-axis, the new coordinate should be x negative y plus rows minus 1. So that's why we get here. So this is how we derive this coordinate. And after that, we still have to rewrite it in the matrix multiplication form because we want to get what is this big M. And basically, you just do some simple mathematics. You will find that, okay, the matrix multiplication is like this. Now, the big M should be 1, 0, 0, 0, negative 1, and rows minus 1. Then we can rewrite it into this matrix multiplication form. So similarly, if you use some similar example here to do the reflection along the y-axis. That is, suppose this is the input image. You do the reflection in this part, in this y, and after that you still need to translate it back to the legal range of x-axis. In that case, we get x prime should be negative x plus columns minus 1, and y prime should be y. Rewrite it into the matrix multiplication form. We get some similar things like this. And after that, actually, we already derived a affine transformation big M for reflection along x and reflection along y. And then we can use the OpenC with the WAP affine to implement it. So this is how we do that. So we get the gray image here. And then we get the shape, again, get the rows column from the gray image dot shape. And then we define what is this big M. So first we do the reflection along x-axis. Then according to what we derived here, this big M should be this 1, 0, 0, 0, negative 1 rows minus 1. And then we get this x-axis reflection from this CV2.WAP affine, give gray image as source, give M, this big M we define here, big M as the transformation matrix, and the output image size should be the columns and rows. After that, we can show the image here. So after reflection along the x-axis, we do it here. So as you can see, it's already flipped. But of course, after flipping, it must shift downward. And for this resulting image is come from the reflection along y. This is we define another big M like this. So it's -1, 0 columns, -1, 0, 1, 0. And basically you do the same thing, give the gray image M columns, rows, and arguments for the web affine and get the reflection image like here. So this is the reflection image along y-axis. So basically, in the original image, you first do the reflection or flipping to this side and then shift it back so that it becomes this one. All right, so any question regarding the image reflection? Great. If no question, then let's take a 5 minutes break. After the 5 minutes break, we will continue to introduce another image affine transformation. That's the rotation.
加了一个平移项，平移项就不是 linear transformation。我看，只有看了我的。差不多行。他还问我那个代码。是他后面的都是应该前面的。是他后面。但是他这个记忆法跑开这么长，非常贴切。真的，你可以自己拿你的教程啊，但那个还叫什么入课吃力，他调化还是有这个那个其实还叫那个名字的时候，那里面发的，我4天。这个太贴切了。
let's continue with the affine transformation. So until now we learned the translation, the reflection. We still have some affine transformation, the rotation. So rotation refers to that now you have a original image and somehow you want to rotate it. Rotate it with some degree, for example, theta. And of course, you also need to define the central point. That is along which point x0, y0 you want to do the rotation. And suppose we have old points xy in the old coordinate system. Now which is rotated along the center of the image. Note that if we want to set the center as the rotation center, then basically it means that you directly find the center of the image, that the midpoint. Then the coordinates after rotation, x prime, y prime will be given by this thing. So here we just omit the derivation here, but yes, if you have learned some geometric knowledge, you actually this is the definition of the rotation. That is, the new x prime should be x minus the center point x0 times cosine theta plus y minus y0. Y0 is again the center point times sine theta, then plus x0. And the y prime should be the negative of x minus x0 times sine theta plus y minus y0 times cosine theta plus this y0. This is the rotation. And then after rotation, we still need to rewrite it into the matrix multiplication form. Otherwise, we can't do the affine transformation. So after rewriting, we find that this matrix big M, this transformation matrix should look like this. Yes, for the rotation, somehow it's like much more complicated than the reflection and then the translation. Previously, if you just do the translation and reflection, basically everything is like you just do some negative sign and add something or minus something. But in the rotation, somehow you must consider that it's rotated by some theta degree. So it's not that you can only move horizontally or vertically. You must consider the angle. So after that, we have the big M like this. And then we can pass this big M to open Seebeck web affine function. So we have the gray IMG here, and we get rows and columns. And then we define the angle that we want to rotate. Suppose now we just want to rotate 45 degrees, but somehow the OpenCV, this web affine, actually it accepts, actually you can also use this 45 degree, but depending on which mathematical library you are using. So here we are using the math library. If we use this math library, then everything we pass into the cosine and sine, these functions, should be the degree in radian. So that's why we have to first convert this angle into math.pi over 4. So we must convert it to radian first. And after that, we get this m. Basically, this m is directly you hard code everything here. But substitute the theta with pi over 4. So after that, we define this big M. Note that actually we also already set the midpoint. The midpoint is that columns over 2 and rows over 2. This is the midpoint or the center we want to do the rotation. Actually, there is another way to generate this transformation matrix, which is very convenient so that you never need to hard code that. So directly from the OpenCV dot get rotation matrix 2D. Actually, in this case, it will directly compute the big M for you. So you only need to first give what is the center you want to rotate along. The center is, for example, this one we just want to rotate along the picture or the image center. So that's columns over 2, rows over 2. And then you need to give the degree you want to rotate, like 45. In this case, it accepts the degree instead of the radian. So this is 45. And this is the scaling factor. We only want to do the rotation. We don't want to do scaling. So we just set it to be 1.0. Means that, okay, now it's just no scaling at all. After that, this get rotation matrix 2B function will directly return the big M for you, the rotation affine transformation matrix, which is very convenient, so that actually you don't need to like hard code everything here. But either way works. they works the same. So after that, you can perform the transformation. Let the rotate 45. This new image be web-affine. Give the gray image as the source, big M as the transformation matrix, and the columns rows as the output image size. After that, you can show the image like this. So as you can see now, the original image rotated 45 degrees to be in this new image, but we didn't change the size of the output image. So as you can see, still it's like 1600 by 1000, this size of the image, and some new pixels occurred. Like this part is some new pixels in the border, right? In the original image, we don't have this part. So all the new part, and this corner is a new part, this corner new part, and this also some new part. All these new parts will by default assigned with the value 0. So that's why all of these 4 parts now directly become black, because they are just accepting the value 0. Some pixels are missing, like this corner is directly missing, and this corner also missing, because we set the output image size to be columns rows, so it must fit into this size, and so some extra pixels will directly be removed in this case. And this is for the rotation. So any question regarding the rotation? Yes, please.
So for the get rotation matrix 2D, is the scaling applied before or after the rotation, or the sequence doesn't matter?
Before the rotation. So we first need to get this big M, and then we do it, the web-affine pass this M to this web-affine function. So
the transformation corresponding to the return the matrix is first we scale it, but is the scaling center point the given center point, or just on default 0, 0?
you mean this center point? This center point, we must specify it.
I mean, we have a scaling factor in the end.
Oh, scaling factor.
Scaling factor.
You mean this scale? Scaling factor. You mean whether the scaling is performed like after rotation or before rotation?
Yeah.
Very good question. I think it's actually it's after rotation. So first do the rotation and then do the scaling.
Is it relative to 0, 0, or the center point provided in the first argument?
Good question. I think I need to further check that. Yeah, this is a very detailed question, like whether the scaling. I think by default, if it follows all of the the formatted procedure, then it should be 0, 0, because this center should only apply for the rotation center. And for the scaling, by default, it should be scaling from the 0, 0 point to the coordinate scaling. A very good question. I think, yeah, maybe I need to check the further details of the documentation. Yeah, but very good one. Yes. Yeah, thank you. Any other question regarding the rotation? All right, if no question, actually that's a very good question about the scaling, because right after we will talk about scaling, but somehow actually we separate rotation and scaling. That means like we didn't consider that, but of course you can follow the procedure. Like if you want to rotate and scale together, you can always like try to separate the 2 steps. Or you can combine the 2 steps using this get rotation matrix 2D. So for this image resizing or scaling, this is a quite simple processing method, but it's a critical processing step in the computer vision, because usually the machine learning models train faster, much faster on the smaller images, and many deep learning model architectures, they just require all of your input images are the same size. But when you collect your data, your raw data, actually they are not in the same size, right? They possibly vary in size. So we have to first do a resizing or the scaling, so that we make sure all of our input data should have the same size, and then they are suitable to fit to some deep learning models, because the deep learning models accept some like fixed size, the same size. So resizing is a common approach to make the input imagery the same size, and it works well unless you have very different aspect ratio from the expected input shape. So let's, by the way, actually resizing and scaling is also a fine transformation. But here we use a different way. That means we are not using the OpenCV swap affine to implement that. We can directly implement it because this scaling is relatively easy. So we can use this resize method. Resize method is specifically for resizing or scaling imagery. In this case, we need to decide these arguments. First, the source imagery, of course, we need to give some input imagery. And the size, again, the size for the output imagery. Basically, this size can already like get some like scaling factor. Then the DST is the output imagery with the size D size. This is optional. It's like you don't need to have to give that. DST is like the destination. Usually you can give some like the name that you want to store your output imagery. And fx and fy, they are some optional. The scale factor alone, the horizontal axis, and the scale factor alone, the vertical axis, usually we don't need to specify them, because actually the function can already infer what is your scale factor by this D size. Because after it accepts the source imagery, it can easily get the size of the source imagery, and then according to your output imagery size, this D size, actually it can already infer what's the scaling factor you want. So usually actually these are all optional. And for the interpolation, again, we need to set some code so that it can restrict the new pixels. Previously, actually we mentioned some extrapolation, right? Extrapolation is that after some processing, you will get some new pixels in the border, and you have to do some extrapolation to assign values to the border. Like the by default way is set all of them to be 0. It's okay for the border pixels because there's some extra outside the imagery, but for some new pixels that will occur inside an imagery, it's not appropriate to set 0. Instead, we use some interpolation to assign the values, and actually there are different codes to do that. Like one of them is to be the inter-nearest. In this case, the new pixels will directly receive values from the nearest neighbor. This is called nearest neighbor interpolation. Another possible way is to do the linear. Then in that case, it will do some bilinear interpolation, so that actually it tries to stretch in a range and then do the linear mapping. And another way is the intercubic. Then in this case, it will do some bicubic interpolation. So still it's some like getting some values through some mapping, but now the mapping is not linear mapping, is some cubic mapping. Note that this interpolation is necessary for scaling. Consider that if you want to scale a small image to a large image, then definitely you will create new pixels. Suppose like you have a 2x2 image, then you only have 4 pixels, but somehow you want to scale it into a 4x4 image. In this case, you will have 16 pixels. That means compared with the previous image, you have 12 new pixels. Then how to assign the values for these 12 new pixels are decided by these interpolation methods. But in this course, we won't cover too much about interpolation. Like we won't require you to give some algorithm to do the interpolation. Basically, you only need to know that there are some ways to assign values for the new pixels. Alright, so this is the syntax for the resize. Let's see the effects. So we read the snowlegs.png and convert it into grayscale, so we get the image like here. Now we want to do the scale, so we directly run this resize, the gray imagery, and we give the output size to be 300, 300, and suppose we just let the interpolation be the linear, and after that we will get the resulting image like this. So as you can see, previously we have this 1600 by 1000 image. After rescaling, the imagery actually we specify it should be 300, 300. So everything is compressed because we do a scaling to a smaller imagery. So basically it still has the same information from the previous imagery, but the coordinates, both coordinates are scaled into this 300 by 300. So this is the scaling. Actually, scaling is also a fine transformation. So that means there is another way to implement it. Of course, you can directly use the resize, but you can also try to think about that. If I ask you to use WAP affine to implement scaling, how will you do that? It's an affine transformation. That means actually you can always find the transformation matrix big M for scaling and then follow the previous way. You can still implement scaling by the WAP affine. Yeah, you can. This will leave you as some after class practice so that you can try to think about that how to use the affine transformation for scaling. All right. So any question regarding the scaling? Okay, great. So I think each time for this lecture, the image processing is basically like a technical report about the OpenCV library. Not much theoretic knowledge, but only how to use the OpenCV's different functions. So it's really some technical report of the OpenCV. But let's continue. So here we will do some summarizations about the characteristics of the image operations. Actually, there are many ways to classify the image operations. So here, one way is based on the region we use to process the pixels. In this case, we can divide them into 3 types. The first is called point-based operation. Point-based operation means that the output value at a specific coordinate is dependent only on the input value at the same coordinate. Basically, it's like this. So one point only depends on some point, the original point in the old image. This is point-based. And another type is called local-based operation. Local-based operation, that now the output value at a specific coordinate is dependent on the input values in the neighborhood of the same coordinate. So if we look at to get the values for this new point, actually we have to consider a small neighborhood here. So that's basically we have to use the values of all the pixels inside the neighborhood to get the new values for one point here. That's the local based. Also, we have some global based image operation. For global based image operation, is the output value at a specific coordinate is dependent on all the values in the input image, like here. So if for any single point you want to decide its value, you have to make use of all the pixels in the original image. Then that is called the global-based image operation. So we can try to look back on what we have learned just now. For example, the conversion, what type of image operation is color to grayscale conversion? I think this is quite easy, right? This is definitely point operation. Because now the output value at a specific coordinate in the new image, in the grayscale image, is only dependent on the input value at the same coordinate of the color image. And for any point here, basically you only need to use of one point in the original image just to convert color into grayscale. So definitely this is a point operation. So actually, we have more point-based operations, like the brightness adjustment, that make the images brighter or dimmer. This is the point-based. And contrast stretching, that adjusts the contrast of images. And also, the gamma correction, that's grayscale nonlinear transformation for the images. Also, the grayscale thresholding, convert the grayscale image into a black and white binary image. And then the histogram equalization, that's a transformation where an output image has approximately the same number of pixels at each grid level. So for our course, we will only cover contrast stretching and grayscale thresholds, these two more point-based operations. For the remaining 3, brightness adjustment adjustments and gamma correction, also histogram equalization. If you are interested in actually the supplementary notes, provided the methods for these 3 imagery operations. So you can check the course website, the supplementary note on the imagery processing. So next we will talk about what is the contrast stretching. Actually, at the beginning of this lecture, I think in last class, I showed you some effects images about the contrast enhancement. That's the same thing with the contrast stretching. So contrast stretching is an imagery enhancement method attempting to improve an imagery by stretching the range of intensity values. And one way to perform such contrast stretching is you can stretch the minimum and maximum intensity values to the possible minimum and maximum intensity values. So here is an example. Suppose 0 to 255, this is the legal range, the standard range, is the standard minimum and maximum intensity for 8-bit images. But however, in your input imaging, it's not necessary to have this range, right? You will have a sub-range in this range. That means in your imaging, possibly the minimum intensity value is a relatively large value. For example, is 100. In your whole image, actually the minimum value is just 100. Actually, it never reaches the value below 100, so it cannot access the value from 0 to 99. In this case, we can try to stretch the minimum intensity value 100 to the possible minimum value 0, because we want to make all of the pixel intensity values quite distinguishable so that we can see it clearly. In this case, we do the stretching. And similarly, if your maximum intensity value in your image is less than 255, you can also try to stretch it to 255. Then what about all the middle values? All the middle values, you can just simply do a linear mapping. This is the general form of the contrast stretching. So for any intensity value, suppose it's I, and then you can get a new value I new using this stretching. The linear transformation is I minus I mean divided by I max minus I mean. Note that this is the range in your raw input image, and then times the new range, because now we want to stretch it into the new range 255, so times this new range, and after that we can get the new value for this I new. So let's see this one. Note that in this one we didn't use any library to do that. We directly do this implementation from scratch, because this is relatively easy to implement, just this function. So suppose our input image is like this. It's a Snorlax low contrast. As you can see, this again, this is a Cabigon. This Pokemon is with so low contrast, actually we cannot see it clearly. Somehow we want it to be clearer to enhance its contrast so that we can see it very clearly. In this case, we do the contrast stretching. We get first we convert all the values from 0, 1 to 0 to 255, because originally this is a PNG image. PNG image means that all the values are between 0 to 1. So first we do this to make it to be the standard legal range, 8-bit data 255. And after that, don't forget that if you use the 8-bit data, all the values, they should be integers. So after we multiply it by 255, actually we also set the type, the array type, to be like the numpy dot integer 8 bits. Okay, after that we find the minimum and the maximum values in this image. We directly get the mean from the numpy.mean, this gray image int, and max from the numpy.max gray image int. And after that, we do the image contrast enhancement or stretching. So this is a direct implementation of the function here. So as you can see, this should be the gray image int minus mean divided by max minus mean, then times 255. After that, we can show the image. The effect is like this. So from the previous low contrast image, now it's like enhanced a lot because actually we stretch the possible range to be like the whole range 255. Previously, actually it's only a very narrow range for the intensity values because the range is so narrow. That's why we cannot distinguish the pixels very clearly. After stretching, like every details now actually is like clearly seen by our human eyes. So this is the imagery, the contrast enhancement or the contrast stretching. So any questions so far regarding the contrast stretching? Great. If no question, yeah, I think the time is almost up. We can just end here today. Next class, we will continue with more technical reports about the OpenCV. So next class, we will continue to introduce the grayscale thresholding. And on next Monday and next Tuesday, please remember to attend the Lab 7 on the imagery processing. And I will see you on next Tuesday's class.